We can get it all down. So this is it's one of those things that like very similar to the NMR stuff. I'm sorry, very similar to the infrared radiation stuff. Obviously, IR uses infrared radiation, and then we talked about how, like, imagine the bonds of springs. You can stretch them and squeeze them and compress them. NMR uses radio waves. So this is
page. Those are longer, right?
What's that?
Those are longer, right? Radio waves.
Yeah, longer wavelength, less energy. Yep. Lower frequency. This starts on page 30. To tell you the truth, it says 35 in your book, but I can't read it on mine. It's chapter 11, and it has figure 11.2. If you're following along with the book.
Figure 11.2.
Yeah, the top of the page says nuclear magnetic resonance. And here's the deal: you can do this with they sit there and say it. Nuclei have atoms with an odd number of protons. So you can do this with hydrogen, carbon 13, chlorine 19, and phosphorus 31. And basically what happens.
This section is, I don't know if we're looking, are you talking about the IB textbook?
Yes.
Yeah, because section 11 is measurement and data processing and analysis.
Yep. So if you go to 11.22 then. Like figure 11.22. Yep.
Oh, I thought you said 11.2.
No. Yeah. Like the figure 11.22.
Yeah, I found it now.
Yeah. So make sure this is what I want to do. Yeah. Notes on NMR. Yeah, HNMR. Let's go ahead and I'll tell you what, this is pretty thick. I don't want to sit there and oversensitize, like, let's go blah with you. I feel like I did that with those organic reactions we did. So I don't want you to feel like, I mean, if you need to take a break or something on this, like basically it's reading the lines just like IR, but there's a lot more different things. So the radio
organic chemistry stuff, I felt like I was doing okay. I'll let you know if I feel like I'm getting a little too much.
So basically what you end up doing is using these radio waves, and then you use two plates, and basically it causes them to spin. And then this spin can be read. And basically, let's see, as it resonates, here we go. It gives us some type of readout. And that's what we're going to be reading are these readouts. And am I sharing? I'm not.
You are not.
I'm sorry.
You've opened breakout rooms, though, it says.
What's that?
You've opened breakout rooms, it says, though.
I thought I closed the breakout.
The host has opened breakout rooms.
Yeah, don't go in the breakout rooms. That was last period. So if we take a look here, basically we're getting this. Now, all that this is going to read for us is all we're doing is HNMR. So all we're talking about are different hydrogens on an organic molecule. All right. So what this technique does is this allows us to read for different chemical environments. So this is what we call our standard.
What does it mean?
Tetramethylsilane. What's that?
What does it mean, different chemical environments?
Okay, so it's kind of funny. So imagine an OH reading would look different than a CH3 reading.
Oh, so like what it's bonded to?
You got it. Yep. So the hydrogen here would come out differently on our reading than a hydrogen here. And then a hydrogen, so instead of a CH3, it will look different than a CH2. And remember, we're looking at the hydrogens. So these two hydrogens will have identical readings. These three hydrogens will have identical readings. And let's say here we have, an aldehyde, that hydrogen will look different than all of these as well. Yay. Right? But that's what chemical environments means. So if we take a look, the NMR basically looks like these lines or these graph lines. And basically it goes from like 0 to 13. So just like the IR spectrum, you had those readings. A basic CH3 won't have much shift from 1. The CH2, the H's here that are attached, the C that's attached to a double bonded O with an ester, they will be at 2 to 2.5. So basically what this does is these H's will shift higher because of the electronegativity of this carbon and this O and this O. So with that in
The more
mind,
electronegative, it's higher.
shift to higher, yep. So with that in mind, take a look here. This H that's attached to a carbon with this double bonded O, you know, this O is pulling this way and that O is pulling that way a little bit, so it's a little bit less, but this one is a 9.4 to 10. And this,
So
these readings right here, you're not going to be able to use these readings very well. These are not the good readings to use. Like if you see these, like, you know, like unless you know that there's a phenyl or a benzene and attached to an OH, you're probably not going to be able to find that reading without finding everything else first. So the ones you want to keep in mind are the ones like this, 2.2 and stuff like that. Now the cool thing is you do have this on page 27 of the IB data booklet. So let's just take a look at one of these and see what we can figure out from it. So if we take a look, we've got our reference at 0, no biggie. Here we have 2 something, and then here we have that 10. So that 10 is basically the highest thing we have up here. So we could have a carboxylic acid or a hydroxyl group, like an alcohol, or we could have an aldehyde. The way you'll know is usually they'll give you something, like they may give you the actual formula, and then you have to figure out where everything goes. So this may say something like C2H4O, and then you would be able to figure that out. Some other things with this is the integrated trace. So that and that ratio tells you the ratio of hydrogens from this peak to hydrogens of this peak. So that distance there and that distance there, if we take that distance and divide it by that distance, we should see that that's probably a 1 to 3 ratio. So the technique that people do is they'll sit there and write 3H and 1H above it. They've actually got it there. So imagine we had C2H4O. Since it's a 1 to 2 ratio, we can imagine that, 1 to 3 ratio, we can imagine that we're going to have at least one CH3. Now, what's telling us that this is not an alcohol? That's a little bit harder. But since we do have that right about 10, 9.4 to 10 tells us that it probably is a double bonded O. Let's just play the idea of maybe it is an alcohol. But the problem with that is we have CH3, CH, OH. What's wrong with this carbon right here?
It's not fulfilled.
You got it. So that's the thing about this. You're almost like a detective. You're like Batman on this. So you'd have to sit there and say, oh, well, it's not an alcohol then. Well, then maybe it is an aldehyde. So then we go ahead and we take a look. Well, let's check. This H right here, well, it's not, it's next to this O that is double bonded. So that is going to be a huge shift. And you can see this little notch right there is telling us that that's on the N. That's the primary, like on the primary carbon. So yeah. So that's going to shift over to the 10 or between 9.4 and 10. And these CH3s here, now the big question is why are they not 0.9 to 1? Now they are bonded to a carbon that's double bonded to an O. And remember how I said that that electronegativity is going to cause that shift to be more than what you're used to. Even though this is a primary, it is bonded to a double bonded O. So that doesn't give it to us, but this right here, it's going to be bonded a little bit. It's going to be shifted a little bit less. And that's why it comes up to about between a 2.3 and 2.5. So that is the basics of it. Let's take a look and see what we got here. So we have 1, 2, 3, 4, right? So that means we have 4 different types of hydrogens. They've given us C3H8O. If we were to draw all of the isomers that we could with C3H0, we could have a primary alcohol. We could have a secondary alcohol. We could have an ether. We don't have a ketone. We can't have an aldehyde because we won't basically, well, one thing you could do is you could use your IDH formula for this. 2N plus 2 minus the number of H's divided by 2. Remember, we don't have to worry about anything else because O doesn't count in this. So our N is 3, so 6 plus 2 is 8. Minus 8 is 0. 0 divided by 2. So our IDH is, our deficit of hydrogens, if you remember, is 0. So that means we won't have any double bonds. So that means this O cannot be double bonded, right? Heavy, right? Yeah. So that means it has to be either an alcohol or an ether. There's only so many places you can put it between 3 carbons. So let's take a look. If we take a look here, and they gave us that that ratio. We have 2 hydrogen, 1 hydrogen, 2 hydrogen, and 3 hydrogen. So if we take a look here, this is probably right at 0.9 or 0.1. That is probably, since it's 3 hydrogens, that's a terminal, I'm sorry.
CH3?
Yeah, CH3, basically a primary CH3. So this has a primary CH3. And this has a primary CH3. We don't count this one, even though it's a primary CH3. It's not going to be at 0.9 to 1.0 because of what?
Because of the oxygen.
You got it. And these guys may not be there as well. Another thing you can do to this is if we take
so why won't those show up?
They will, but they will shift over. They won't be at 0.9 to 0.1. They'll be a little
not for that one, for the middle one.
Because this O being attached to that C may shift them over as well.
So it even affects those?
I'm sorry?
I didn't realize it would affect the hydrogens if they're bonded to a carbon which is bonded to an oxygen. It's quite a...
Yeah, it'll sit there and even, yeah, that pool in electrons will affect it a little. It may not affect it a huge amount, but you can see that this is right at 0.9 to 1.0. Now, the fact that we have these four different things means we have four different type of H's as well, right? So if we take a look, every H right here is exactly the same. It's bonded to a carbon that's bonded to CH2, right?
Yeah.
There is something called the spikes, and you see how these spikes are a little bit different?
Yeah.
Yeah, so there's a rule called the N+1 rule. And that's your number of, yeah, that's good, silly, but that's your number of neighboring carbons. I'm sorry, neighboring how do we say this? The hydrogens on your neighboring carbon. Hydrogens neighboring on neighboring carbon. So that is 2 + 1. So if we see this spike right here, it will be what we call a triplet. It would have basically like three types of, like you'd be able to see three peaks. So this carbon right here, so there's, let's call that A. Let's call these hydrogens over here B. Both of these are identical. How many hydrogens are neighboring on their carbons?
5.
1, 2, 3, 4, 5. So 5 + 1 is
6.
6. So that would be a sextuplet. So it would look similar to that, you know, when everything was said and done. Do you think you can identify that one?
The next one over. It has 2.
Yeah. So there's our two H's that it's talking about. Right? What about this one?
That one's a lot
1,
thinner,
2,
but it's
right?
so
So if we
it's
take a look,
probably the next one.
yeah. So if we take a look here, here we have 1, 2, we'll call this C. Since these hydrogens, even though they're on a CH2, they are different than the hydrogens on this CH2, right? What is their spike going to look like?
Thin.
Yeah, so it would be 3. And here we have an H over here, right? So this H right here only has 1 spike. And this one is all by itself as well. So we would say we have A, B, C, and D. So if we were to look at this diagram, it would have to have, if it were this compound, 4 spikes. And then we would be looking for 1 with 6, 1 with 3, 1 with 3, and then 1 with 1. This one right here, well, if we bisect this like that, look at its symmetry, these hydrogens here and these hydrogens here would be the same. We can call them both A. And we would have, instead of 3 hydrogens on our spike, we would have how many?
6.
6, right? So right here, that's one way we could get this one off immediately because we don't have something with 6. If we take a look here, this would be B. When we take a look here, this would be C. So we only have 3 spikes on this one. uh, the methoxyethane. Here's our meth. Here's our ethane. Here's our oxy. So here we have A. That would be 3 H's. It's got it there. And then we would have 1 spike. And here, that would be B with 2 H's, and it would have 4 spikes. And here, this would be C, and it would have 3 spikes. And there would be 3 H's. Again, we only have A, B, and C. So the only one that fits this is the propanol. So we can draw those isomers involved. We should be able to identify the substance. At 0. Yeah, that would be like a multiple choice question, you would think, or maybe not. But that is a memorization. That's the TMS, or tetramethylsilane. It's a silicon-based instead of a carbon-based chemical. Identify the unknown compound from the number of peaks. Okay, so we did it. We went a little further, but 4 peaks. Don't ever include the TMS. So this one is the only one that has 4 peaks. Identify the group responsible for the signal at 0.9. Don't forget, you would have this sheet right here. And if we take a look, CH3, primary usually is 0.9.
Mr. Jackson?
Yeah.
All right, I'm back.
Oh no, you left me.
Yeah, our power went out for like half a second, so my internet just stopped working. Did you just keep going?
Yeah, I had no clue. I was just going through how we could get each of these questions. So since it's C3H8, you should be able to draw these 3 isomers. The substance at the peak is that the TMS. You're going to have to just have that memorized. It's a silicon-based versus carbon-based, so it's still going to have the 4. And then the tetra means 4, methyl, and then it's silicon-based, so it's silane. That may be like a multiple choice question or something like that. I don't you know. But yeah, that'd be a silly one to miss. Then it says identify the unknown compounds by the number of peaks. But we did that. We went a little bit more into the information than we needed to, but this was the only one that should have 4 peaks. And apparently they call them peaks instead of spikes. So I'll try to change my my vernacular or whatever to that. Every other one here had 3. And then identify the group responsible for the signal at 0.9. Well, that's that primary alpha carbon. The H is on the primary alpha carbon. We had 2 of those, actually 3 of those, but we felt that these would be shifted a little more. This one may be shifted slightly, but yeah, maybe not that much. But these guys probably would be shifted. When I say shifted, instead of showing up at the 0.9, they may be like 1.2 or something like that. Boom, boom, boom. You still there? Now I'm going to be checking you for a second. So if we take a look here, page 41. I'm sorry, question 41. So they tell you the shift and they tell you the peak area. Now the peak area is that hydrogen number.
So by the way, like I tried to like find these questions on my book so I could kind of like look at it on my book as well, but I couldn't, so I was looking at the screen. Do you know where in the book this is?
Yeah, let me find out real quick. I just gotta grab a book. Page 379.
370. Okay, yeah, I see it.
Yeah, cool. Sorry about that. All right.
That's fine.
So if we take a look here, yeah, I made a copy so it'll lay flat so it'll look better on the screen, but it didn't copy those pages down there because this book is weirdly shaped. So if we take a look here, identify the compound from that. Well, how many, and we're just in the splitting patterns.
What?
I'm just trying to think, and they say peak area. So that actually may be the splitting patterns. We'll see in a second. Don't worry about it. It may not be the hydrogen number, in other words. It may be the splitting patterns. We'll figure that out in a second. So let's take a look and let's just identify what peaks we would expect to see from this compound. So if we had CH3, CH2, CH3, how many different types of hydrogens do we have?
CH2, CH2.
2, right? These are the same. We'll call them A, and this would be B. So if we were to take a look then, what would the carbon height be for the 6 H's versus H2? Well, we would see a 1, now I'm just doing height here, a 1, 2, 3, right? Now, let's do this. Let's go ahead and put maybe what this is, the splitting patterns are those little peaks I told you about. So for the CH2, how many hydrogens are on its neighbors?
6.
So that means we have how many?
7.
Yep. So you would see that many peaks on that line, 7 little peaks. And for each of these, how many peaks?
3.
3. So for this one, we would see it around 0.9 to 1. For this one, if we take a look, there's actually a better set on your thing. We would see that one around 1.3 to 1.4. This is, I'm sorry, this is that data booklet that I gave you a copy of. I don't think you printed it though.
That's quite a bit of ink.
Yeah. What I would print for it is basically the IR and the NMR and the mass spectral if you're having trouble with that. But all the rest, it's very similar to the AP guide. It's got a lot more like tables to read from, where the AP guide, I think, would just give you the section of the table you need, but yeah. All right, so we know it can't be this because this only has 2. How about this one?
3.
Yep. So let's take a look here. We have C, C, C. I think this is double bonded O and then H. All right, so this one right here, we would see, compared to all these, we would see 1 to 2 to 3 for the height or the like the integration. This one we would see 3 peaks. This one we would see 4 peaks. And this one we would see 1 peak. Right?
Yeah. So can't be that one either.
Can't be that one. Another reason it can't be this one is that aldehyde. If we look at our chemical shift for that aldehyde, let me describe it here. Where's the aldehyde? I don't have it on here. I think it's like 10. I think it's similar to this, like 10. It's like, it's high. I don't see it for some reason though. Is it on the other one? Ah, here it is. 9.4 to 10. So we don't have anything in that range, so it can't be that guy either. How about this one?
3.
3. So if we take a look. 1, 2, 3. Here again, we would have, let's go ahead and just draw it out. CH3, CH2, C, CH3. So we have 1, 2, 3. Here we would have 3 peaks. Here we would have 4 peaks. Here we would have 1 peak.
So it can't be that one.
Can't be that one. It looks like we're looking
How
at this.
convenient.
How
Right
could
one
we-
is the last one that we look at.
Yeah, right? Unless we made a mistake over here. Hopefully not, though. So if we take a look here, these two will be A.
Same.
They're the same. These two would be B. And this one is, let's see. Right?
Yeah.
Yeah. And the weird thing is, and maybe it's because I'm not sure what this peak area is, but this would be 3 for both of these. For this one, we actually have 6 for the B's. Now I'm getting a little bit nervous that I don't understand what they mean by this peak area. And for this one, we would have 5. Well, that's some garbage right there. That means we overlooked something on one of the other ones. But
Oh, no.
what's that?
Oh no.
Oh no.
I jinxed us when I spoke.
So so this one, the 1 and the 2.0 makes sense. Let's just let's take a look. Maybe we need to look closer at what this chemical shift is for 2.3. Maybe I need to relook up what they mean by peak area. Look at that. We're probably looking at a ketone because that goes from 2.2 to 2.7. What the heck do they mean by peak area then? Because they say splitting patterns here. Let's try that.
Does it provide you the answer? Do you not have like a teacher's
I
guide?
do. Let me grab it real quick. Oh, maybe I'll bring it over. Maybe I'll make a bunch more mistakes. Let's recount those on that because with that, knowing that that 2.3 is there, knowing this 2.3 is here, that may be a better lookout for that double bonded O. But this peak area, it should be 0, right? 1, 2, 3, 4 bonds, 0 plus 1. So I'm not sure what they mean by peak area being 2 there. But
Well, why would the peak area be 4 for the second carbon? Oh wait, never mind. Never mind. I just
3 plus
answered my
1,
own
right?
question.
And then, yeah, so I'm trying to figure out what peak area means, which is, it's weird. Oh. No. Because then if it was ratio, it would be 3 to 2 to 1, right? 3 to 2 to 1. I'm sorry. 3 to 2 to 3. There we go. Is it this one or this one? It's this one, right? There we go. Okay. I'm sorry. 3, 4. 1. So that's the whenever they say splitting patterns, I'm sitting here thinking they mean these. 1, 2, 3. I think what they are doing is they're doing the ratio of hydrogens. So they shouldn't have said splitting patterns, because look at the ratio of hydrogens here. 3 to 2 to 3. Let's make sure these work again. This would probably be 1 point. No, that's because we would assume that this one right here. Yep. Okay, there we go. Yeah. So being next to this O would shift it over. And then this CH2 next to that. CH2 next to that is going to be the 2.3. Yuck. Peak area apparently means ratio of hydrogens. So let's take a look. If we take a look here, identify Y. So we have fuel Y is shown. We only have 2 peaks. And it looks like a 1 to what? That's what they're talking about. A 1 to what?
I'm a little confused. Sorry.
No worries. So peak area, basically what they're talking about is how much area is this peak taking versus how much area is this peak taking.
So it's not the width. It's
well, it may be the width,
I mean,
right? We take a look here.
That would make sense with area, but I don't know.
What's the, is it, if this is 1, what is this?
More than 1.
Okay, good. What I think what they're talking about is the area under, like, basically how high did this go up versus this one. If we just knock that there and knock
like
that
that's
there,
like 3 times then.
yeah. So it's a 1 to 3, right? Yeah, and I'm sorry that it doesn't actually look like this book is going into the split. Which that's why that confused me whenever I read this as saying splitting. We'll go into that again. We'll go into that on our own then. They have it here though. That's so funny. Oh wait, no, that's different. That's the mass thing. Yeah, they don't have any splits at all in here. It's ridiculous. All right. Okay. So this is a 1 to 3 ratio. The fact that we have 2 peaks, I think that this may just be one of those things of where, you know, they want you to be able to say, okay, this has 2 peaks. So which of these has 2 peaks?
Out of the 40 question 41.
For 42.
42. Okay.
Yeah.
Well, the D Well, not D. No, never, not D. Never mind.
Yeah, how many peaks would D have?
1.
One. Good. Caught yourself.
Or it's C.
Let's check C. CH3. CH2. OH. How many
I
H?
have 3.
That would have 3.
It's A then.
It's A then. It has to be A. Good. We have the.
I can't get it wrong 3 times in a row. Not today.
So if we take a look, that makes sense to us because we have a 1-to-3 ratio as well. And that's what peak area means. 1-to-3. How many peaks will each of the following have? Will this be 1 or 2?
2.
2. 1 or 2?
1.
1. Because they're the same, right? You could cut it in half and it's the same thing. 1, 2, or 3?
2.
2. These two are the same and this one is different. 1, 2, 3, or 4?
That one has 1.
1.
Because they're all the same.
Good. All right, describe the spectrum. Describe and explain the H-NMR spectrum of CH3, CH2, OH.
It's going to have 3 peaks. because
3
there's
peaks.
3
Okay.
different types of hydrogen. I mean, like, of course, not sure if it's necessarily necessary, but with the N+1 rule, the first group of hydrogens is going to have a split of 3.
All right.
And then the second group is going to have one of 4.
All right. So where is that
Or
one?
would the OH fine?
If it's a CH2 on an OH, somewhere between 1 and 6, right? Let's just put it right in the middle of 1 and 6. We'll put it right at 3.5. So you said it would have, what's that?
I didn't say anything.
Oh, you said that these guys had 3 plus 1. 4.
So yeah, it'd be 4.
Good. And
This last one would have just 1.
1. Let's find out where the H from an OH goes. The H from an OH. Let's check here. Do they have a better H from an OH? Between 1 and 6. What did I put for the other one then? I put the CH2 connected to an OH. Well, they don't have a good listing for this. We know it's going to be pulled a little bit more. Let's put that one at 2.5, and then we'll put the other one way over there. 1, 2, 3, 4. And then our last one, we said we only need 1. So it looks something like that, right?
Yeah.
What's our ratios though? We didn't do ratios well.
I mean, the first one's going to have the lowest one with 4 is going to have the lowest one with 3 is going to have a really high ratio because it's 3.
And then this one
is going to be 2.
Yeah.
And then
this one will be
OH is going to be 1.
And with that, they can, if you're drawing this, you can sit there and just put 1H, 2H, and 3H. And that will get you past the requirement of having to get that size. Because basically you're showing that you know that. You're showing that ratio. that make sense? Wow.
What?
As I'm looking, yeah, I don't see. I only see a few things. We'll continue this next time. I'll try to get some examples and stuff like that. But I'm going to put one question on. You don't have to do it if you don't have time. I know you're busy, but I'm going to try to put one question from the IB test onto the Canvas. I'm going to put it for today. And if you just want to take a look at it, if you have the time just to read it, don't spend much time on it if you don't have the time. But I just want you to show, like, they want to be able to give you the IR and the HNMR and like the mass and stuff like that, and have you be able to figure out everything about it and then write the formula for it. So we need to make sure that we can get the information we need from these in order to be able to do that. I'm going to put it on there. I want you to take a look at it if you have the time, and then we'll go from there. If you don't, then we'll look at it on Tuesday. Like we said, the only thing that you know, is going to take time that you need is that paper. For
Yeah.
All right. I will see you tomorrow morning for a review.
Right.
You have any questions for me?
Just a quick clarification about scheduling. So Monday we don't have any classes for anyone.
Yeah, we don't have anything. Yep, it is Martin Luther King Day.
All right.
Cool. And well, it doesn't matter to you, but they've been talking about Saturday having a surprise or a special quorum to determine if we are actually going back on Tuesday, if half the groups will be coming into school.
Yeah, well.
Yeah,
It'll be interesting.
I agree. I mean, what did we reach yesterday? Almost 5,000 people dying in one day, according to the data, according to the numbers, according to the media. But yeah. All right, man.
Well,